Good afternoon, February 12, 2015. This is MATB110, Section 1, Calculus 1. Today is day number 12, into week number 6, the week just before the Chinese New Year's holiday. So let's get started. First of all, I go back to this last class before the Chinese New Year's holiday. Remember, this past Monday, we visit section 3.5, your chapter 3, where we would like you to understand something about the maximum and the minimum of the values and how to find those values. And if you haven't paid attention to the website this week, you can actually come here, come back here to click on those links. These are the tutorial links to help you refresh the memory on those specific points. And it's very useful. And also for this on the inverse functions. So make sure you make the best use of them. Just as a quick review, this is the kind of video you can expect from the Khan's Academy. Okay, it's the kind of tutorial video. For those of you who have not touched them before, expect that this could help you quickly remember something.
Well, think about it. When this function is of maximum values and minimum values, and for the sake of this, we can assume that the graph of this function just keeps getting lower and lower and lower as x becomes more and more negative, and lower and lower and lower as x goes beyond the interval that I have depicted right over here. So what is the maximum value that this function takes on? Well, we can eyeball that. It looks like it's at this point. It looks like it's at that point right over there. So we would call this a global maximum. A global maximum. The function never takes on a value larger than this. So we could say that we have a global maximum at the point x naught. Because f of x naught is greater than or equal to f of x for any other x in the domain. And that's pretty obvious when you look at it like this. Now, do we have a global minimum point the way that I draw it? Well, no. This function can take on arbitrarily negative values. It approaches negative infinity as x approaches negative infinity. It approaches negative infinity as x approaches positive infinity. So we have, let me write this down, we have no global minimum. Now let me ask you a question. Do we have local minima or local maxima? When I say minima, it's just the plural of minimum, and maxima is just the plural of maximum. So do we have a local minima here, or local minimum here? Well, a local minimum, you can imagine, means that that value of the function at that point is lower than the points around it. So right over here, it looks like we have a local minimum. We have a local minimum. And I'm not giving you a very rigorous definition here, but one way to think about it is, we can say that we have a local minimum point at x1 is if we have a region around x1 where f of x1 is less than an f of x for any x in this region right over here. And it's pretty easy to eyeball too. This is a low point for any of the values of f around it right over there. Now, do we have any other local minima? Well, it doesn't look like we do. Now, what about local maxima? Well, this one right over here, let me do it in purple. I don't want to get people confused, actually, let me do it this color. This point right over here looks like a local maximum. Local, not lox, that would have to deal with salmon. Local maximum right over there. Local maximum. So we could say at the point x1, at the point x2, we have a local maximum point at x2 because f of x2 is larger than f of x for any x around a neighborhood around x2. I'm not being very rigorous, but you can see it just by looking at it. So that's fair enough. We've identified all of the maxima and minima, often called the extrema, for this function. Now, how can we identify those if we knew something about the derivative of the function? Well, let's look at the derivative at each of these points. So at this first point right over here, if I were to try to visualize the tangent line, do that in another color than brown. If I were to try to visualize the tangent line, it would look something like that. So the slope here is 0. So we would say that f prime of x naught is equal to 0. The slope of the tangent line at this point is 0. What about over here? Well, once again, the tangent line will look something like that. So once again, we would say f prime at x1 is equal to 0. What about over here? Well, here, the tangent line is actually not well defined. We have a positive slope going into it, and then immediately jumps to being a negative slope. So over here, f prime of x2 is not defined. Let me just write undefined. Undefined. So we have an interesting, and once again, I'm not rigorously proving it to you, I just want you to get the intuition here. We see that if we have some type of an extrema, and we're not talking about when x is at an endpoint of an interval, just to be clear what I'm talking about when I'm talking about x as an endpoint of an interval, we're saying, let's say that the function is, let's say we have an interval from there, so let's say a function starts right over there and then keeps going. This would be a maximum point, but it would be an endpoint. We're not talking about endpoints right now. We're talking about when we have points in between, or when our interval is infinite. So we're not talking about points like that or points like this. We're talking about the points in between. The points in between. So if you have a point inside of an interval, it's going to be a minimum or maximum, and we see the intuition here. If you have, so non-endpoint, min or max at, let's say, x is equal to a. So if you know that you have a minimum or maximum point, at some point x is equal to a, and x is at the endpoint, x is at the endpoint of some interval, this tells you something interesting, or at least we have the intuition. We see that the derivative at x is equal to a is going to be equal to 0, or the derivative at x is equal to a is going to be undefined. And we see that in each of these cases. Derivative is 0, derivative is 0, derivative is undefined. And we have a word for these points where the derivative is either 0 or the derivative is undefined. We call them critical points. We call them critical points. So for the sake of this function, the critical points are, if we can include x sub 0, we can include x sub 1. At x sub 0 and x sub 1, the derivative is 0, and x sub 2, where the function is undefined. Now, so if we have a non-endpoint minimum or maximum point, then it's going to be a critical point. But can we say it the other way around? If we find a critical point where the derivative is 0 or the derivative is undefined, is that going to be a maximum or minimum point? And to think about that, let's imagine this point right over here. So let's call this x sub 3. If we look at the tangent line right over here, if we look at the slope right over here, it looks like f prime of x sub 3 is equal to 0. So based on our definition of critical point, x sub 3 would also be a critical point, but it does not appear to be a minimum or a maximum point. So minimum or maximum point, that's not an endpoint, it's definitely going to be a critical point, but being a critical point by itself does not mean you're at a minimum or maximum point. So just to be clear, at all of these points, we're at a minimum or maximum point. We're at a critical point. All of these are critical points, but this is not a minimum or maximum point. In the next video, we'll start to think about how you can differentiate, or how you can tell whether you have a minimum or maximum at a critical point.
You see that it's very concise. It answers all the questions and ways to you at the end of the Monday class. What are the critical points? What's the characteristic of those points? And what if define a critical point? Is it necessary a maximum point or minimum point? So you can visit this particular video. It's very concise, just 9 minutes, and it clears the picture. So the next thing you need to do is definitely to look at how we're going to find the critical points. Okay? Five minutes.
Let's say that f of x is equal to x times e to the negative 2x squared. And we want to find any critical numbers for f. So I encourage you to pause this video and think about, can you find any critical numbers of f? So assuming you've given a go at it, so let's just remind ourselves what a critical number is. So we would say C is a critical number of f, if and only if, I'll write if with two f's, short for if and only if, f prime of C is equal to 0, or f prime of C is undefined, So if we look for the critical numbers for f, we want to figure out all the places where the derivative of this with respect to x is either equal to 0 or it is undefined. So let's think about how we can find the derivative of this. So let's see, f prime of x is going to be, well, let's see, we're going to have to apply some combination of the product rule and the chain rule. So it's going to be the derivative with respect to x of x, so it's going to be that, times e to the negative 2x squared plus the derivative with respect to x of e to the negative 2x squared of e to the negative 2x squared times x. So this is just the product rule right over here, derivative of this, of the x, times e to the negative 2x squared, plus the derivative of e to the negative 2x squared, times x right over here. So what is this going to be? Well, all of this stuff in magenta, the derivative of x with respect to x, that's just going to be equal to 1. So this first part is going to be equal to e to the negative 2x squared. And now the derivative of e to the negative 2x squared over here, this is this pink color, so this part right over here, that is going to be equal to, or just apply the chain rule. Derivative of e to the negative 2x squared with respect to negative 2x squared, well, that's just going to be e to the negative 2x squared. And we're going to multiply that times the derivative of negative 2x squared with respect to x. And so that's going to be what? Negative 4x. So times negative 4x. And of course we have this x over here. We have that x over there. And let's see, can we simplify it? Can we simplify it at all? Well, obviously both of these terms have e to the negative 2x squared. I'm going to try to figure out where this is either undefined or where this is equal to 0. So let's think about this a little bit. So let's see, if we factor in e to the negative 2x squared, put that in green, we're going to have, this is equal to e to the negative 2x squared times, we have here 1 minus 4x squared. 1 minus 4x squared. So this is the derivative of f. Now, where would this be undefined or equal to 0? Well, let's see, e to the negative 2x squared, this is going to be defined for any value of x. This part is going to be defined. And this part is also going to be defined for any value of x. So there's no point where this is undefined. Let's think about when this is going to be equal to 0. So you have this product of these two expressions equaling 0. E to the negative 2x squared, that'll never be equal to 0. If you get this exponent to be a really, I guess you could say, very negative number, you will approach 0, but you'll never get it to be 0. So this part here can't be 0. But if the product of two things are 0, at least one of them has to be 0. So the only way that we can get f prime of x to be equal to 0 is when 1 minus 4x squared is equal to 0. So 1 minus 4x squared is equal to 0. Let me rewrite that. 1 minus 4x squared is equal to 0. When does that happen? And this one we can just solve. Add 4x squared to both sides. You get 1 is equal to 4x squared. Divide both sides by 4. You get 1/4 is equal to x squared. And then, what x values is this true at? Well, we just take the plus or minus square root of both sides, and you get x is equal to plus or minus 1/2. Negative 1/2 squared is 1/4. Positive 1/2 squared is 1/4. So at x equals plus or minus 1/2, f prime, or the derivative, is equal to 0. So let me write it this way. F prime of 1/2 is equal to 0, and you can verify that right over here. And f prime of negative 1/2 is equal to 0. So if someone asks what are the critical numbers here? Critical numbers, they are 1/2 and negative 1/2.
So you got it? This is very good illustrations of the basic techniques of finding critical numbers. And we need to see one more, how to test the critical points for local extreme. So this is examples in your quiz questions, right? So let's go for it, just a couple of minutes.
In the last video, we saw that if a function takes on a minimum or maximum value, min-max value for our function at x equals a, then a is a critical point. Then x equals a is a critical point. But then we saw that the other way around isn't necessarily true. X equal a being a critical point does not necessarily mean that the function takes on a minimum or maximum value at that point. So what we're going to try to do in this video is try to come up with some criteria, especially involving the derivative of the function around x equals a, to figure out if it is a minimum or a maximum point. So let's look at what we saw in the last video. We saw that this point right over here is where the function takes on a maximum value. So this critical point in particular was x naught. What made it a critical point was that the derivative is 0. You have a critical point where either the derivative is 0 or the derivative is undefined. So this is a critical point. And let's explore what the derivative is doing as we approach that point. So in order for this to be a maximum point, the function is increasing as we approach it. The function is increasing is another way of saying that the slope is positive. The slope is changing, but it stays positive the whole time, which means that the function is increasing. And the slope being positive is another way of saying that the derivative is greater than 0 as we approach that point. Now what happens as we pass that point? Right at that point the slope is 0, but then as we pass that point, what has to happen in order for that to be a maximum point? Well, the value of the function has to go down. If the value of the function is going down, that means the slope is negative. And that's another way of saying that the derivative is negative. So that seems like a pretty good criteria for identifying whether a critical point is a maximum point. So let's say that we have critical point A. We are at a maximum point. We are at a max if f prime of x switches signs from positive to negative, as we cross x equals a. That's exactly what happened right over here. Let's make sure it happened at our other maximum point right over here. So right over here, as we approach that point, the function is increasing. The function increasing means that the slope is positive. It's a different positive slope. The slope is changing. It's actually getting more and more steep, or more and more positive, but it is definitely positive. So it definitely means, so it's positive going into that point, and then it becomes negative as after we cross that point. The slope was undefined right at the point, but it did switch signs from positive to negative as we crossed that critical point. So these both meet our criteria for being a maximum point. So far, our criteria seems pretty good. Now let's make sure that somehow this point right over here, which we identified in the last video as a critical point, let's make, I think we call this, this was x0, this was x1, this was x2, this was x1, this was x2, so this is x3. Let's make sure that this doesn't somehow meet the criteria, because we see visually that this is not a maximum point. So as we approach this, our slope is negative, and then as we cross it, our slope is still negative. We're still decreasing. So we haven't switched signs. So this does not meet our criteria, which is good. Now let's come up with a criteria for a minimum point. and I think you could see where this is likely to go. Well, we identified in the last video that this right over here is the minimum point. We can see that it's a local minimum just by looking at it. And what's the slope doing as we approach it? So the function is decreasing, the slope is negative as we approach it. F prime of x is less than 0 as we approach that point. And then right after we cross it, this would be a minimum point if the function were to keep decreasing somehow. The function needs to increase now. So let me do that same green. So right after that, the function starts increasing again. F prime of x is greater than 0. So this seems like pretty good criteria for a minimum point. F prime of x switches signs from negative to positive as we cross A. If we have some critical point A, the function takes on a minimum value at A if the derivative of our function switches signs from negative to positive as we cross A, from negative to positive. Now once again, this point right over here, this critical point, x sub 3, does not meet that criteria. We go from negative and to 0 right at that point, then they go to negative again. So this is not a minimum or a maximum point.
So you got this revisions clarifying? All right. So lastly, let's visit this minimum and maximum for specific functions. Very much like the quiz question you finished.
We've got the function f of x is equal to x to the third power minus 12x plus 2. And what I want to do in this video is think about at what points does my function f take on minimum or maximum values. And to figure that out, I have to first figure out what are the critical points for my function f, and then which of those critical points do we achieve a minimum or maximum value. And to determine the critical points, we have to find the derivative of our function, because our critical points are just the points at which our derivative is either equal to 0 or undefined. So the derivative of this thing right over here, we're just going to use the power rule several times, you can call it the constant rule, but the derivative of x to the third is 3x squared, derivative of negative 12x is negative 12, and the derivative of a constant doesn't change with respect to x, so it's just going to be equal to 0. So we're going to get a critical point when this thing right over here, for some value of x, is either undefined or 0. Well, this thing is defined for all values of x. So the only places we're going to find critical points is when this thing is equal to 0. So let's set it equal to 0. When does 3x squared minus 12 equal 0? So let's add 12 to both sides. You get 3x squared is equal to 12. Divide both sides by 3. You get x squared is equal to 4. Well, this is going to happen when x is equal to 2 and x is equal to negative, and x is equal to negative 2. Just to be clear, f of 2 is equal, or let me be clear, f prime of 2, you get 3 times 4 minus 12, which is equal to 0, and f prime of negative 2 is also, same exact reason, is also equal to 0. So we can say, and I'll switch colors here, that f has critical points at x equals 2 and x equals negative 2. Well, that's fair enough, but we still don't know whether they're minimum point, whether the function takes on minimum values at those points, maximum values at those points, or neither. To figure that out, we have to figure out whether the derivative changes signs around these points. So let's actually try to graph the derivative to think about this. So let's graph. So I'll draw an axis right over here. I'll do it down here, because maybe we can use that information later on to graph f of x. So let's say this is my x-axis, this is my y-axis, and so we have critical points at x is equal to positive 2, so it's 1, 2, and x is equal to negative 2. 1, 2, x is equal to negative 2. So what does this derivative look like if we wanted to graph it? Well, we have when x is equal to 0 for the derivative, we're at negative 12, so this is the point y is equal to negative 12. So we're graphing y is equal to f prime of x. So it'll look something like this. it will look something like this. These are obviously the zeros of our derivative, so it has to move up to cross the x-axis there, and over here, and over here. So what is the derivative doing at each of these critical points? Well, over here, our derivative is crossing from being positive, we have a positive negative derivative, to being a negative derivative. So we're crossing from being a positive derivative to being a negative derivative. That was our criteria for a critical point to be a maximum point, or being a maximum point. Over here, we're crossing from a negative derivative to a positive derivative, which is our criteria for a critical point for the function to have a minimum value at a critical point. So a minimum. And I just want to make sure we have the derivative, we have the correct intuition. If some function is increasing going into some point, so if it's increasing going into some point, and at that point we see actually we have a derivative of 0, the derivative could also be undefined, we have a derivative of 0, and then the function begins decreasing, that's why this would be a maximum point. Similarly, if we have a situation where the function is decreasing going into a point, the derivative is negative. Remember, this is the graph of the derivative. Let me make this clear. This is the graph of y is equal to not f of x, but f prime of x. So if we have a situation where going into the point, the function has a negative slope. We see we have a negative slope here, so the function might look something like this. And then right at this point, the function is either undefined or has 0 slope, so in this case it has 0 slope. And then after that point, let me do it right under it. So going into it, we have a negative slope, and then right over here we have a 0 slope, which I can draw even better than that. So you would imagine going into it, we have a negative slope, right at that point we have a 0 slope, and then we have a positive slope. So the function begins increasing. That's why we say we have a minimum point right over there. So what I did right over here is to try to conceptualize what the function itself could look like given the derivative, in this case switching from a positive derivative to a negative derivative across that critical point, or going from a negative derivative to a positive derivative. That's why this is the criteria for a maximum point, this is the criteria for a minimum point. But with that out of the way, can we use this intuition that we just talked about to at least try to sketch the graph of f of x? So let's try to do it. Let's try to do it. So let's try to do it. And it's just going to be a sketch. It's not going to be very exact, but at least it'll give us a sense of the shape of what f of x looks like. So my best attempt. So it might not be drawn completely to scale. So it's my x-axis. This is my y-axis. We know we have a critical point at x is equal to positive 2, and we have a critical point at x is equal to, and we have a critical point at x is equal to negative 2. We know just from inspection that the y-intercept right here, the graph of y is equal to f of x, when x is 0, f of x is 2. So we're going to hit right over, let's say we're going to hit right over, I don't want to draw this completely to the same scale as the x-axis. So let's say that this is 2. Let's say that this is 2 right over here. So this is where we're going to cross. This is going to be our y-intercept. And so we said already that we have a maximum point at x is equal to negative 2. So what is f of negative 2? f of negative 2 is equal to 8, or negative 8, let me be careful, it's negative 8, and then we're going to have 12 times negative 2, which is negative 24, but then we're going to add it. So we're subtracting negative 24, so this is plus 24, and then we finally have plus 2. So negative 8 plus 24 plus 2, so that's going to be negative 8 plus 24 is 16, plus 2 is 18. So f of negative 2 is equal to 18. And I'm not drawing it completely to scale, but let's say that this is 18 right over here. So this is the function. This is the point negative 2, comma 18. And we know that it's a maximum point. The derivative going into that point is negative. The derivative going into that point is negative. The derivative going into that point is positive. So we are increasing. The slope is positive. And then after we cross that point, the slope becomes negative. The slope becomes negative. The derivative crossed the x-axis. the slope becomes negative. Actually, I want to use that same color. It looks like this. It looks like this. And then, of course, the graph is going to cross it's going to have a y-intercept, something like that. And then, as we approach 2, we are approaching another critical point. Now, what is f of 2? F of 2 is going to be equal to positive 8 minus 24 plus 2. So this is 10 minus 24, which is equal to negative 14. So let's say this is the point negative 14 right over here. Check it out a little bit. Let's say this is negative 14. So this is f of 2 right over there. And we saw already that the slope is negative as we approach it. So our function is decreasing as we approach it. And then right there, the slope is 0. We figured that out earlier. That's how we identified it being a critical point. And then the slope is increasing after that. The derivative is positive. The slope is increasing. So this is our sketch of what f of x could look like, given that these are the critical points. We were able to identify we were able to identify 2 as a minimum point. So this was a minimum value. The function takes on a minimum value when x is equal to 2, and the function took on a maximum value when f was equal to negative 2.
You see the excellent illustrations help you understand first the critical points, second, where the critical points are minimum or maximum, and then how you will find them given the particular functions. Now, I believe this is a very good revision for the work on sections 3.5, including a very good illustrations of the problem you have finished on yesterday's quiz. Now, let's get back to the very important topic of this week, okay? Better say this particular class. Well, let's get back to our little environment first. Okay, great. So here we go. Let's get back to calculus 1. Remember, on Monday, we helped you to get back to the highlight calculus through Professor Gilbert Strand's interpretation of the maximum and the minimum, okay, which is located in week number 5, before class material, okay? We have already done the before class material for week number 6, which you can also refer to. So 2 basic topics we would like to revisit. The first one is the maximum and minimum, and the second derivative, which is well handled on this Monday and included in your test a little bit. And today we would like to revisit again another topic which has been covered last Thursday by Professor David Jerrison's on exponential functions. This is a very interesting way to listen to the interpretation by Professor Gilbert Strand. Now this is a very important part of the revision because after today we will say goodbye to chapter 3, and when you come back after Chinese New Year's holiday, it's the beginning of chapter 4, and we are going to deal with the very last sections on chapter 3 as if it's part of chapter 4, okay? So listen again to Professor Gilbert Strand's exponential functions. This is part 3.8 in your chapter.
Well, this is Exponential Day, the day for the function that only calculus could create. Y is e to the x. And it couldn't have come from algebra, because however we approach e to the x, there's some limiting step. Something goes to 0, something goes to infinity. We've got different ways to reach e to the x, but all of them involve that limiting process. which we haven't discussed in full. Let me come back at a later time to the whole theory, discussion of limits, and just go forward here with this highly important function. And I'd like to start with its most important property, which is, so it has this remarkable property that its slope is equal to itself. That's what is special about e to the x. Its slope is equal to the slope is equal to the function. Now, I have to admit that if we had a function like that, y equal e to the x, then 2e to the x would work just as well, or 10e to the x. Those would, the factor 2 or the factor 10 would be in y, and it would also be in the slope, and it would cancel, and this is a differential equation, our first differential equation. A differential equation is an equation that involves, as this one does, the function and the slope. It connects them, and that's the fantastic description of nature is by differential equations. So it's great to see this one early, and it's the most important one. When you get this one, you've got a whole lot of others solved. Okay, but I needed to give it a starting point so that the solution would be e to the x and not 10e to the x. So where shall I start it? Well, if I want it to be an e to the x, then when x is 0, e to the 0 power, some number to the 0 power, is always 1. So let me start this. Y equals 1 at x equals 0. Differential equations, you have to tell where they begin. So that's our starting point. And you see what this means? This means that it starts at 1, and what's its slope at the starting point? The slope is also 1, so it's climbing. As it climbs, so y gets larger because it's got a positive slope. As y gets larger, the slope gets larger, so it climbs faster. And then it's gone higher, y is bigger, the slope is equal, so the slope is also bigger, so it climbs even faster. It just takes off. It climbs much faster than x to the 100th power. You might think y equal x to the 100th. That's climbing pretty well. 2 to the 100th, 10 to the 100th, but no way, it doesn't come close to keeping up with y equal e to the x. Okay, I've got several things to do, and one more thing I have to do. This is a key property, but there's another key property that is true for any 2 to the x, 3 to the x, e to the x. And that key property is also to show, I have to show this, that my function, e to the x, times e to the possibly a different x, is equal to, do you know what we want here? This has got to come out of the construction, out of this property. It's got to come, but we want this to deserve to be called some number to the x power. If we take some number x times and multiply it by that same number, capital X times, then we've got that number how many times? X plus capital X. This is 1. So that's a key property to be proved. So what will I do? Let me summarize in advance, outline in advance. I'm going to construct this function from its property. Then I'm going to check that it's got this property, that important equality there. Then, of course, I'll graph it, I'll figure out what E is, and I'll say something about cases where this comes up. Oh, I could even say something right away about where does this happen, that growth is equal or proportional to the function itself. It happens with interest, with money in a bank. When you get interest, the interest is proportional, of course, to the amount there. And if they add that interest in, if you don't take it out and spend it, but you compound it, put it in there, then you have more money. When they compute the interest again, it's computed on that larger amount and is more interest than the first time. And so it goes. So that's, money in a bank is a case, it's a case of exponential growth. I mean, a hedge fund grows faster than our bank account does, but all following e to the x. If you just hang on long enough, you're way up there. Okay, so here's my job. Follow this rule and start at y equal 1. So can I just do it this way? Here's my function y of x that I want to construct. I want to build that function, and I know that it starts at 1, but it's going to do have some more things. Now this has to equal dy dx. These have to be the same. That's my rule. So dy dx is going to start with a 1. But now I can't stop, because if the derivative is a 1, I have to put an x up here so that its derivative will be 1, right? Its slope will be 1. That's a steadily climbing x whose slope is 1. But now these are supposed to be equal again. So I have to put this x also here. But now I've got to add something more on the top so that the slope will be 1 plus x. The slope of the x was 1. What do I need here to give the slope to the x? Remember, x squared had the slope 2x. So I need half of x squared so that I'll have 1x. So I need a half of x squared. Good. The slope of that is this. But I'm also trying to get the two to be equal. So I have no choice. I have to put in the 1/2 x squared there. You see, I'm never going to catch up. Or only if I go forever. That's the point. I'll have to go forever. And what will the next one be? Oh yeah. If you see the next one, then we can see the pattern. So it's going to be, now what am I doing? This one has to have this slope. I'm trying to I'm fixing the top line now. If I'm aiming for a slope of x squared, then I need some number of x cubes. So how many x cubes do I need? Well, I need to know what's the slope of x cubed. The rule for powers of x to the n, is n times one smaller power. The slope of x cubed is 3 times x squared. So I better divide by that 3. So that the 3 cancels the 3. Now the slope of that, the 3x squared, the 3's would cancel and I get x squared, but I'm looking for 1/2 x squared. I need also a 2. You see that it's 1/6 of x cubed that's going to do the job. 1/6 of x cubed. Because the slope, the 3 cancels the 3, and I wanted to end up with a 2. And now, you know what's coming? These are supposed to be equal. I have to have this 1/6 x cubed down here too. And I never get to stop. Can you see, we have to see, okay, what is a typical, after I've done this, say, n times, I'd like to have some idea of what is it when I get up to x to some nth power, then it's multiplied by some fraction, and I'm looking to see what is that fraction. What is that fraction? And then, of course, they'll all show up down there again. Well, if you see this pattern, this was 3 times 2. You could say 3 times 2 times 1. This one was 2 times 1. This one was just 1. It's n factorial. N factorial is what I need. I need n times n minus 1. I need all these numbers all the way, and I'll throw in the 1 at the end. And I have to put the mathematicians' take it away symbol, the little 3 dots that mean don't stop, keep going. But do you see that this will be okay? This is called n factorial, x to the nth over n factorial, because when I take the slope of x to the nth, an n will come down, cancel that n, x, I'll have it 1 lower power. You see, when I take the slope of this, I'll have the n will cancel the n, so I'll still have these other guys down below, and I'll have x to the n minus 1, and that will be x to the n minus 1 over n minus 1 factorial. That will be the previous one. But now I have to add in the x to the nth over n factorial, because y and dy dx have to be the same, so I have to keep going. Okay, so you might say, well, you're going to blow up. Not personally, the series. But what saves you? What saves you is the fact that these n factorials, those fractions, that n factorial gets to be really large, really fast. Faster than this x to the nth could grow. So altogether, these terms, x to the nth over n factorial, they get extremely, extremely small. And then this series of things comes, it comes to a limit. It doesn't keep going, getting bigger and bigger and bigger as I add more terms, because what I'm adding is so small, so small. And that's the point where we have to discuss limits later. Okay, so that's my construction. Construction complete. The function y of the exponential function, e to the x, this is e to the x, is being defined by 1 plus x plus a half x squared plus a 6x cubed, and so on. Okay. I've got a function, now its property. And the key property is this. Can I move to the next board? So the next step is check, well, I've asked you. I've got e to the x. And let me write again what it is. 1 plus x plus a half x squared plus 1/6 x cubed, and so on. And then I've got e to any other power, or even the same power. 1 plus, I'll just use capital X for this power. 1/6 of capital X cubed plus so on. And I want to multiply those and see what I get. Okay, I apologize. Here I ask you to believe in this infinite series, and kind of a little dodgy, but it works. And now I ask you to multiply 2 of the things. You may say, okay, you're asking a lot here, but go, just hang on. Let's multiply these. E to the x times e to the capital X. Because that's what I'm interested in knowing. Okay, Can you just do all the multiplications? So, and we'll see what we get. Okay, so 1 times 1 is 1, no problem. 1 times x is the x. 1 times this x is the big X. Now, can I keep going, all right? Well, 1 times a half x squared is, and now I have a x times a big X. And now I have a 1 times a half big X squared. And more, of course. Notice the way I'm doing it is like I'm keeping all the things that have 2 x's together. And then I would keep all the things that have 3 x's together, and so on. Now, what is it that I'm hoping? I'm hoping that this is the same as the series for x plus capital X. Okay, what's that? That's my exponential series, and every time I have to put in x plus capital X. In other words, of course, it starts with 1, then it has the x plus capital X, and then it has the 1/2 of x plus capital X squared, and it keeps going. And I just want you to say yes. I guess I hope you say yes when I ask, is this big multiplication the same as this one? Well, I think it is. Let's start the check anyway. The 1s are good, the x and the x. I'm really just putting parentheses around now I'm going to put parentheses around all the second degree terms and say, is that the same as that? Yeah, this is the critical point here. Do we at least start out correctly? So you have to remember how do you do, but of course you do remember how to multiply x plus capital X by itself. You just do the multiplications. X, when I multiply that by itself, I get x squared. With a half, I get that. And then you remember how many x times x's do I get? Little x times big X, or be 2 of those. But then the 1/2 factor leaves me with 1, and that's what I want. And then finally, this guy by himself, squared, is the 1/2 capital X squared that I also want. So far, so good. Do you want to see the cube terms? I don't, well, I'd rather you did it, but I should at least show that I'm willing to try. So what do I mean by the cube terms? I mean that here I want to get the next one should be 1/6 of x plus x cubed. And from the multiplication, I get some separate pieces. I get 1 times this, I get a 6. When I do that multiplication, I get 1/6 x cubed. And then I maybe get some 1/2 x squared times x. Oh, you see why I would rather you did this. But I'll finish this little line. There's also a 1/2, an x times 1/2 x squared, so that's a half of x times the big X squared. And then there is the 1 times the 1/6 x cubed. So those are the 4 pieces that come third degree when I do the big multiplication, and they have to match the third degree term in the last line. And they do match. If we cube thing, do you remember the right words to say now? Binomial theorem. The binomial theorem tells you how to take the nth power of a sum, like x plus capital X, to the nth power. It tells you all the many pieces you get, and those many pieces are exactly the pieces that we get directly by multiplying that line by that line. So the binomial theorem at long last pays off and confirms our great property here. So this is a big deal. Okay. So let me now come back here. Having checked that. I wanted to say something about this series. 1 plus x plus a half x squared, where the typical term is x to the nth over n factorial. This is the, I would say, the second most important infinite series in mathematics, the exponential series. And it's the way I wanted to construct e to the x by matching term by term and seeing that these n factorials show up. But you might want to know, what's the most important series? Reasonable question. For me, the most important series would be the one looking like this, except it doesn't have the fractions. For me, the most important series would be the one, I'll slip it up here, 1 plus x squared without the half, plus x cubed without the 1/6, plus so on, plus x to the n without this n factorial that's making it so small. Can you see this? 1 plus x squared plus x cubed plus x to the n? That, I think it's called the geometric series, powers of x. Now, it's simpler because it doesn't have these fractions. But it's riskier because those fractions were making the exponential series succeed. Whereas here, with the geometric series, well, look what happens when x is 1. When x is 1, we have 1 plus 1 plus 1 plus 1 plus 1, forever all ones, it blows up. And when x is bigger than 1, that series blows up even faster. So this series, the geometric series, this most important one, does succeed, but only for x, only when x is below 1. X equal 1 is the cutoff, and it fails after that. There is no cutoff for that exponential series because of these dividing by these bigger and bigger numbers. This works for all x. Okay, so those are the two series. Okay. Now, what happens? So, let me ask you, what happens if I put x equal 1 in the exponential series? That gives me e to the first power, which is e. So finally, you may say, this is rather late in the day, I'm going to figure out what e is from this series. Put in, set x equal 1, and you learn that e to the first power, which is e, is, can I just put it in? 1 plus, x is 1 plus 1/2 of 1 squared plus 1/6 of 1 cubed. What's the next term in this? So these are numbers now, and I'm getting a number. I'm getting this incredible number e, named after Euler. Euler was a fantastic mathematician. I think he wrote more important papers than any mathematician in history. So he was allowed to name this number after himself. E. E-U-L-E-R, his name is spelled. Okay, what's the next term? This is 3 factorial, right? 3 times 2 times 1. The next term will be 4 factorial. I'll multiply that by 4. It'll be a 24th. And then times 5, 120th. And so on. They're getting Well, what can I tell you about this number? It will be a definite number. It's more than, well, it's certainly more than 2.5, because I start with 2.5 here, and then I add these. Well, I could even throw in 1/6. That's more than 2 2/3, would that be? If I quit here, I'd have 2 2/3, and then I get a little more. It's easy to show. No way you would reach as far as 3. These later terms are dropping too fast. And actually, the number turns out to be, so it's 2 point something, let's see, a little more than 2 2/3, so it's around 2.7. But it's not exactly 2.7. In fact, it's not exactly any fraction or any finite decimal. It goes on and on. 1, 8, 2, 8, something. I think there are like more 8s than you'd expect right here at the beginning, but then in the long run, not. In the long run, yeah, so that's the number E. Okay. Oh, so now we know E. We know e to the x, we know E, we know this thing. I should draw a graph, right? That's the other thing you do with a function, is draw a graph. Okay, so here's a graph. This is x. Let me put in x equals 0 here and x equals 1 here. And this is going to be a graph of e to the x. And at x equals 0, what is it? We started with that. It should be, so this is y, I'm graphing y, and it starts at 1. That's what we said. At x equals 0, I've started at 1 with a slope of 1. So I have a slope of 1, but the slope is climbing up, and it reaches here. That height is what? E. That height is E. So, because when we said x equal 1 here, we got E. So it's climbing, 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 and now what about on the other side? That had a slope of 1, so it's more like that. Now what about when x is negative? When x is negative, this is a highly useful fact. Suppose, well, I want to think about e to the minus x. Well, now let me just take capital X to be minus little x. So I get e to the x times e to the minus x. What is that? What does that equal? If I multiply e to the x times e to the minus x, as usual, I'm supposed to add these. I get 0, so I get e to the 0, which is 1. In other words, e to the minus x is 1 over e to the x, which we fully expected, so that at x equal minus 1 here, I'm down to 1 over e, 1/3 approximately. So it's going down. This is, in this way, it's decaying very fast. It almost touches that line, but never quite. This way, it's climbing. It's growing really. Well, it's growing exponentially. And that's what its graph looks like. And now I would like to connect back at the end of this lecture to the insurance business, to the interest business, the bank compounding interest. Can I take your time with that important example of the exponential function? And we'll see a new way to reach e. I like this way. I like the way we did it with the infinite series. But here's another way. So, suppose you're getting 100% interest. Generous bank. Okay. So then, and you start with $1 at 100%. 100%. And the bank gives you interest at the end of every year. So at the end of the first year, you had $1 in the bank. It adds in 100%, it adds in another $1. So now you've got $2 in the bank after the first year. At the end of the second year, it gives you 100% of what you've got in the bank, so it gives you 2 more, it gives you 4. At the end of the third year, it gives you an additional 4, you're up to 8, and you see what's happening. It's the powers of 2. Well, that's pretty good growth. But it's not calculus. Calculus doesn't do things in steps of a year. Calculus says, cut that step down. I mean, you would want to ask your bank, couldn't you just, like, figure the interest a little more often? And put it in there, like figure it every month? So what would happen if you figured the interest every month? Of course, you wouldn't get 100% interest in a month. You'd get 100% divided by 12. Because we're only talking about 1 month. So if it was months, you start with 1. You have 1 plus 1/12. That's what you'd have after a month.
It's going to be very
Now,
interesting.
what would you have
applications of that, but because of the time, I need to cut it off here and let you go home and finish watching the rest of this. It's easy to get back to this video because it's already there in our before class activity of last week and this week. Now allow me to take attendance, and after that, wishing you a very healthy Chinese New Year's holiday. And I think it's very good conclusions of the first half of our course today. Okay, here we go. Nikki, thank you. Jerry, thank you. Eden is not here today. Okay. And then Jason is not here today too. Kurtwin, thank you. Jan is not here today. Okay. And then Amy, thank you. Susie, thank you. Bob, thank you. And then Vivian, thank you. And Strong, are you here, Strong? Not here today? Okay. Nisho, are you here? Okay, thank you. So Nisho, that's it, right? Thank you. Yuan, thank you. Sue, thank you. Pete, thank you. Elaine, thank you. Ken, thank you. Alphys is not here today. Anson, yes, you're here. Caesar, thank you. Oh, okay, good. Jason is here, thank you. And then Alex, thank you. Tina, thank you. Gao Chun, are you here? Oh, okay. Thank you. Xin Han, are you here? Not here today. Kin, not here. Simon, not here. Okay. William, thank you. Stain, not here today. Esther, not here today. Ida, thank you. So, Maine, thank you. Fora is not here today. Logo is here. Thank you. Jackie, thank you. And then Amber, thank you. And Kay is not here today. Happy Chinese New Year. Okay? Thank you very much. So that's it for today's MATB 110, Section 1, Calculus 1 on February the 12th, 2015. Until after the New Year's holiday, stay tuned.